Very good. Okay, so first of all, welcome all. I'm super happy that many people are joining. And just a little overview of what is this seminar series. We were thinking in the DDA in New York, like possibilities or efforts that we can do to make the DDA more accessible and more welcoming for all the students, young postdocs and young faculty, and all the senior faculty as well, to make a more a community friendship as well, and that will lead to collaborations and more healthy environment for all of us. So we are pulling these seminars as the second one, so we are very happy that you are all joining. And today we will have Professor Ting is an assistant professor at the University of Toronto. Professor Ting grew up in Shanghai, China, where she completed her bachelor's degree at the Fudan University with a major in physics and minor in diplomacy. She received the Erasmus Mundus Scholarship for a joint European master program in space science and technology, and she earned her PhD from Texas A&M University in 2016. And then she was elected as the 2016 recipient of the Leon Lederman Fellow at the Fermi National Accelerator Laboratory. She was a NASA Hubble Fellowship Program, Einstein Fellow, and Carnegie Princeton Fellow at Carnegie Observatories in 2019 and 2021. And we are very happy to have her here. So welcome, Professor Ting. She's going to talk about the impact of the LMC infall in the Milky Way satellites and their tidal streams. That will be the first part of the talk. And as the second part of the talk, she will share her experience and obstacles as a female non-native English speaker and first-generation college student with a F1 visa enrolling a PhD program in the US. Just a little reminder about these programs, these seminars. The idea is like the first half an hour, we have a scientific talk where the speakers share like what is their science and so on. And the second part of the series is to share and to talk about DEI issues in our community and share our experience. So we are very happy to have you, Ting. So go ahead.
Thank you, Santiago, and also thanks, Juliet, for the invitation and organization for this wonderful seminar series. And it's my pleasure to give a talk here. So I'm Ting Li at University of Toronto. So I'm going to start with my science talk. So just to be, I don't know if I will call myself dynamicist. I work on a lot of galactic dynamics, but I'm not a theorist. I'm doing more observational related things. And I collaborate with a lot of people doing modeling. And some of this work I will show in the next 30 minutes are how we learned about the Milky Way and the impact of LMC infall onto the Milky Way and impact on the Milky Way satellites. I hope you will enjoy the talk and learn something, and maybe also interested in doing some of the modeling work using the observational data we have here. So we all know that, and feel free to raise your hand anytime. I can monitor the screen, and I'm happy to pause and answer any questions. So we all know that LMC is entering Milky Way, and it's the first infall that bringing, it's also the small Magellanic Cloud and Large Magellanic Cloud together. And this is the view in the hydrogen neutron hydrogen map, but we all know that the two satellites are bringing a few other small satellites, and it also impact our Milky Way. So I do want to first start with saying that a lot of work I'm showing is going to from my collaboration, namely the Southern Stellar Stream Spectroscope Survey, or S5, and the people I highlight here in yellow are the postdoc or student in this group that probably you will see them in the job market already now or soon. A lot of work also cannot be done without the awesomeness of them. Okay, so give a bit of background about the impact of LMC. So this is probably something you have heard about how the LMC infall impact on the Milky Way halo. So last time, I think Catherine Johnson talked about the disequilibrium in the disk and seeing these phase-based spiral, and here we are talking about what the LMC causing the equilibrium in the Milky Way halo. So this is a work done by Nicole Garavito Camargo in 2019 on the left and 2020 on the right. The idea is the LMC come in, and due to the dynamic of friction, so this is a trajectory of LMC. I hope you can see my cursor. due to LMC come in, that at the path it goes through, it will have a cluster of dark matter due to dynamic friction. And also there will be a collective response. This is what we call LMC wake or transient wake. And then there's also another collective response on the other side of the Milky Way that will have the response for this infall. So in short, the Milky Way is not in dynamic equilibrium anymore. Also, the center of the Milky Way is not really the center of Milky Way, but the barycenter of LMC and the Milky Way disk. So this is what we think that would be because of the infall LMC. And actually, there's some observations to support that theory. So here, what you're seeing is from some simulation work on the right and the observational data on the left that showing you what the halo density would look like because of this impact of LMC infall. So what the perturbation in the density could come from. So this is a simulation showing you there's some overdensity and there's some underdensity. And we more or less see such kind of structure in the data. So this is done by Charlie Conroy's group. And in the kinematic space, oh, sorry, I didn't correct for these. These should be kinematic perturbation or velocity perturbation. So in the velocity space, we also see something similar. Again, here is the model on the right and the data on the left. What you see is the velocity in galaxy standard rest. So again, because the Milky Way is not in dynamical equilibrium, you expect the bulk motion of the star in the halo is moving in one direction for part of the sky, and then in the other direction in the other part of the sky. And this is actually seen more or less from the data, but I think we do definitely have more to do to get a better measurement on this. So this is a work done by Dennis Urkel and their collaborators. So we actually see from the density, from the velocity, that the halo of our Milky Way is impacted by the infall of LMC, and there is a good match between the theory, the model, and observation. And the next question I want to ask is, what about the impact on a Milky Way's companions? Not just the halo, but the satellites, goblet clusters, and the stellar streams. So the next, I want to first talk about stellar stream to start with, but I'll touch also the galaxies later. So for the stellar streams, first I want to show this movie for those who don't work in this field to know what are these. So we all know that Milky Way-like galaxies are assembled by creating and the disrupting of smaller systems, like the disrupting galaxies, small galaxies, dwarf galaxies in our Milky Way, or global clusters. So stellar stream is a special phase, I would say, between those clusters or galaxies are started being disrupted, but not fully phase mixed yet. So we see these kind of linear structure on the sky and coherent structure on the sky share some common kinematic and chemical properties. So we have seen many of these streams since I think since more than 2 decades now. I think this year is am I correct? This year is the 2 decades of the Sagittarius. No, next year probably is the 2 decade of the Sagittarius stream discovery. There should be some celebration on that. And so we see some of these stellar streams from this is the Sloan Digital Sky survey view in the northern hemisphere. And in the southern hemisphere, I involved in also some work from the southern hemisphere in the dark energy survey. We find all these stellar streams. And that's where I started this S5 and try to follow up them and study them. So these are a map of the stream we have followed up spectroscopically to get their kinematics and try to use them for doing some dynamical modeling. And I will start with talking about this longest one in my data. That's not Sagittarius. That's a stream called often Chenab stream. It covers over about 200 degrees on the sky. So it has a complicated name because it was discovered as first called orphan stream because it was a first stream that had no progenitor identified, not like a Sagittarius stream has an obvious Sagittarius dwarf galaxy progenitor. Orphan stream has no progenitor identified, so it was called orphan. And on the sky, it was originally discovered. Let me show. It was originally discovered this part of the sky in the Sloan Digital Sky Survey. And later on, there is another stream and then people extended to somewhere here. So extended to something above the galactic plane. So this is called orphan stream for over a decade now. And then several years later in the dark energy survey, we find another stream called Chenab stream in the DS footprint, the dark energy footprint, which is the gray color, the shade here. And so we thought it was a different stream, so we called it a Synapse stream. But later, that through the R-Lyrae stars in Gaia DR2, we found that this is one stream at a very long that connect in the southern hemisphere and northern hemisphere. And why we did not connect them the very beginning when it was discovered, partially because all these surveys are not fully covered, but even when we find the two streams, we should be able to check the orbital pole and say, okay, they may be connected. But that was never thought of when we discovered these. The reason is shown in this plot. So this is showing the orbital pole of the stream. So every particle on the stream, we can calculate the orbital pole, right? So this is the longitude and this is the latitude. So this is what happened to the often north. We call it often south at that time, but that's basically Shenab. So the north part is this part, and then the southern part is this part. So you can see the orbital pole from one part of the stream to another part of the stream change by like 20 degrees on the sky. And usually if you think about a stream in an orbit without any perturbations, it should be, if it in a spherical potential, it should always have the same pole. If it has some triaxial halo, then we'll have some precession. But we never thought about a big pole shift in the inclination. And that actually is because of the perturbation from LMC. So this is another way to see it from the observational data. So here what you're seeing is a stream of often Synapse stream in the north, and then in the south is the Synapse that I mentioned. So you can see in the north part, the motion, the proper motion of the stream, more or less along the track of the stream. So the stream is moving along the stream, which makes sense because that's how the stream forms, right? The stream should form along the motion of the stream. But in the southern part, you can see the proper motion of the stream is almost perpendicular to the track of the stream. This misalignment basically is showing that there is external force that drag the star so that the star is moving in this direction, but the stream is in this direction. And that's evidence. And later with the proper motion data and with also the track, but without the velocity, because that time we don't have the radial velocity, we were able to at least put some kind of constraint on the showing that LMC have to be included. If there's no LMC, then this is what we expect the trajectory of the stream on the sky. But including a LMC, then we can kind of more or less explain where the location of the R-Lyrae stars in the often Synapse stream. And later, when we get the full 60 data that from S5 last year, we were able to do a much better modeling for the Milky Way potential and LMC potential simultaneously with the data. So here's a movie showing you what's happening. So the stream was formed, often Synapse stream from tidal disruption, and so far it's all good. But then as time goes, the LMC comes in, and then the southern part of the stream get pulled and form this kind of twist in the stream. And that's what you see, the misalignment in the motion and the trajectory on the sky. This is not only happening in the often Synapse stream. It's the longest stream and it's the most obvious one, but we also see such things in many other streams in the southern hemisphere where the LMC is close to. So this is a work led by Nora Ship, currently a postdoc at MIT. So she did this work when she was a graduate student at UChicago, where I overlap. And you can see that she measured the track of the stream and then proper motion, average proper motion of the stream. And you can see many of the streams show a misalignment between the proper motion, the motion, and the track. And some of those are because they are closer to, either they are closer to the LMC at some point, or because their speed is relatively slow compared to LMC relative to something else. So that's why they have a higher impact. So like Aleka Uma has a much higher misalignment here. The Synapse is what I talked about often earlier, also has a big misalignment. So these are what we studied. And then we can also use the full 6D from on sky position, the distance, the proper motion in RE-DEC or in 2D, and the velocity to fit the data, fit the model with our data. So here in this movie, you will see the red points are the data we got for often Synapse stream in 5D here plus the stream longitude. So in 6D, and then the best fit model. So what you are seeing here is over the past 2 giga-years, how the stream moves in the final observational space frame of the stream, and how eventually match with the data. And you can see the this part get pulled up. And we only have data in this movie, we only have data so far till here about 5.1, longitude 5.1, I think this 5.1 about something around -70. And if the model is correct, we'd expect to see a strong kink here that is deviate from the original track of the stream. That what we think. So this natural prediction, we actually are getting data. We are actually already got the data for this part, and then we can use them to see if matches with the model, and also whether we can get better constraints on the Milky Way and LMC potential. That's kind of what we are doing. We can use this stream to constrain the Milky Way and LMC simultaneously and to measure the dynamical friction because of when the LMC comes in, because LMC put a huge impact on these stellar streams. Another thing I want to mention is about perturbations in energy and angular momentum space. Many people always say, oh, energy is conservative or angular momentum is conservative for these streams, so we can use them for like the clustering to measure the potential of the Milky Way, for example. But this is what we get in the energy and angular momentum space for this often Schnapp stream, starting from 5.1 of -70 to about +100. And you can see that both the energy and angular momentum change dramatically. And this actually is also naturally predicted by our model with the data fitting. So what you are seeing again is the same movie as before, how the evolution of the stream is in the angular momentum and the energy space. And there is a leading arm and a trailing arm. And then it's getting slightly bigger because there's slightly different energy. But then what you will see in the next 2 seconds is there will be huge perturbation in the energy and angular momentum space because of the perturbation from the LMC. And this is what make it comparable to what we are seeing now. So again, this is data, or the dots here is the data, and then the shaded region on the back histogram, the 2D histogram on the back, in the back is what we see from the best fit model that I showed earlier from the data. So again, we want to be caution that because of the LMC infall, a lot of the stream is also not really conserved in energy and angular momentum space. So a lot of things people are using doing substructure, using like finding the using ELZ space to find a different substructure. You might heard about a lot of these substructures found by different groups. They are just doing this clustering in the angular momentum and energy space. They also be cautioned that that might not be true, because we know that LMC is making a huge impact on these. Okay, so I talk a lot about on the stellar streams. So what about the satellites? So I'm going to show a few other examples on the satellites. First is about the orbits of the satellites. So we know that Milky Way has a lot of dwarf galaxies or satellite galaxies orbiting around us. And here is a work led by Andrew Pace, a postdoc at Carnegie Mellon, that's showing that before, without and with LMC, how much the pericenter and the apocenter could change if you do not consider the LMC, but you should consider LMC in. So the LMC did have impact on some of the dwarf galaxies. These are the ones with the apocenter or pericenter change by more than 25%. And the other example I want to show is another particular awesome dwarf galaxy called Antillia 2. Antillia 2 have almost the same size as LMC, but it was not discovered until about 3-4 years ago after Gaia DR2 release, because it's super diffuse, super low surface brightness. And it believed that it's under tidal stripping. That's why we didn't, and it's also because of the location that close to the galactic plane. So it's had been hiding for decades. So this is what we know about the Antillia 2. This is basically how it looks like in terms of stellar density on the sky in RA and the DEC. Its current distance is about 130 kiloparsec. It's pretty far, but it's believed to have the tidal disruption because it has a pretty small pericenter in the past. We also observed from S5, also observed the velocity, alongside velocity as a function of the semi-major axis here, and we find a very convincing velocity gradient that's showing these galaxies under tidal stripping. But one puzzle here is that it seems the proper motion vector of this dwarf galaxy, which is showing in orange here, doesn't match with the elongation or the ellipticity of the dwarf galaxy, which is showing as the gray here. There is an angle there. And I mean, we know that the proper motion should be roughly aligned with where the particles sprays out or disrupted. So if we take the dwarf galaxy and then we put it in some modeling and then try to see where the stream would be, it should be these contours that in bluish. So it doesn't align with the elongation that we are seeing here from Antillia 2. So what is causing this mismatch? It turned out to be the answer is LMC. If we consider the particle spray, like having particle leaving from the tidal radius of the galaxy, but including the LMC into the consideration, then it will have a perfect match that the elongation we are seeing here from Antillia 2 is a result of tidal disruption. So we are seeing this elongation actually matches the proper motion after we included LMC. So the proper motion of the Antillia 2 didn't change, but what we need to include is a motion of the LMC, the motion of the Milky Way, okay, with respect to the LMC infall, the reflex motion come from the LMC infall, and that will be able to correct for that. And that is the impact of LMC to this dwarf galaxy. So it's not saying the LMC is changing the trajectory of those dwarf galaxies here. It's more saying because the Milky Way is not in dynamical equilibrium, our center is not center of the whole system, and there is some vector kick from the LMC infall to the Milky Way that causing this misalignment. And then I want to finish my talk on the last question I have is, we always talk about dwarf galaxies has triaxiality. Some of these dwarf galaxies looks elliptical because they live in a triaxial dark matter halo, because dark matter, a natural prediction of CDM is they will form triaxial dark matter halos. And when a galaxy forms in this triaxial dark matter halo, we see that they are elongated, they are elliptical. But I really want to ask if that's really the case for Milky Way satellites, or these are a result of tides. This is not really very polished. My next part is more a question to the group, and maybe if someone's interested, I'm happy to talk more and maybe form a collaboration for a future paper. So I want to start a bit about a few of these examples. So I've already talked about Antillia 2, although the proper motion vector and the elongation vector, right? One is the motion vector, one is the what we call the morphology vector, doesn't align to each other. But after you consider LMC, you can make it work for Antillia 2. So the elongation of Antillia 2 can explain by tidal disruption. How about for other ones? So this is, oh, sorry, I didn't label them. This is Carina dwarf galaxy. This is Hercules dwarf galaxy. These are all the satellite galaxy in our Milky Way. And it was detailed in this paper in case people are more interested in. And here the vector we are showing in orange are the motion vector for the proper motion. So you can see these two galaxies are both elongated, and the motion vector matches with the elongation vector. So maybe it is saying that the galaxies here are elongated because a result of tides. However, there are not always like that. So here we try to measure, again, the motion angle. The theta mu is the proper motion vector, and then theta xy is the elongation vector. If they're aligned, it should be 0. Right? If it's misaligned, then it should be some number larger. And here y-axis is the ellipticity. So if it's 0, it's a circular. If it's larger than 4.5, then it's pretty highly elongated, elliptical. So you can see for most of the elongated one, they have a relatively small angle between the motion vector and the morphology or elongation vector. It's not always true for all of them though. For example, this is a big one, and here it's just showing you the histogram for all the high elliptical ones. So it's a bulk here from all the realization. This one, I cannot explain it, that if we say all of the high elongation or elliptical galaxies in our Milky Way is a result of tides. So let's take a look what this one is. So this one is rectangular 2. So rectangular 2 is this outlier that the proper motion and the elongation doesn't align very closely. It's not to have a small delta theta. And you can see here, this is the ellipticity of a rectangular 2 dwarf galaxy. This is the vector of motion, or the other arrow is the direction to the galaxy center. Sorry if it's confusing, but the orange vector is the proper motion. And so you can see this big angle about 60 degrees, which is what we are seeing here. So so what I had in the past summer is I had an undergraduate student from University of British Columbia working with me. She trying to run this spray particle model using GalPy for all the dwarf galaxies in the Milky Way. And this is what she find. If you don't have LMC considered here, then this is a vector of the proper motion, and the spray particle should be along this direction in orange. But if we consider LMC into it, like what we did for Antelope 2, this is what we expect the spray particle would be, which matches with the elongation here. So almost I can explain, except for this one, which it's complicated because this is a satellite of LMC, or believed to be a satellite of LMC. We almost can explain all the high elongated satellite in our Milky Way almost align, or say the elongation can explain by some kind of tidal disruption. I think this is a very preliminary study, and I think there need to be more sophisticated n-body simulations to answer this question, whether that's true or not. To that end, I think that's all for my science part of the talk. And I want to make sure I share with you not only that LMC is impacting our Milky Way halo, it also impacts a lot of the substructures and satellite galaxies and companions in our Milky Way through like the stream, by the change of orbital pole, also by like the misalignment between the motion and the trajectory, and also the impact on the satellite galaxies in our Milky Way, like the orbits, and also the location of the tails around of the dwarf galaxy on the sky. Okay, that's all what I wanted to share in the science part. I hope it's not too much, and I'm happy to take any questions.
Okay, Juliet, you have a question, right?
Yes. So first of all, thank you for the wonderful talk. I did not know about the Orphan Shinab stream, and it's so cool. I was wondering if you could go back to the plot where you showed the kink that you were going to do follow-up observations to better constrain.
Yeah.
As a planet dynamicist, I don't know too much about these observations, but I'm curious, like, is the reason that you don't have members of the kink part just because you haven't identified like what the cluster members are? Like, what type of observations do you have to do to identify the stars in that region?
Yeah, that's a very good question. So first of all, when we find these stream, and it's not all about the stream I'm talking about here. We start usually with a photometric survey, imaging survey like this. We measure the stellar density on the sky and then see this over density form a linear structure. That's how we find them. And then what we do is we follow up with spectroscopic surveys to identify individual members, to measure their kinematics in a 6D. That's what we get for example, this model here. I will stop here. But then why we did not do this part is simply because if you look in two reasons. One is I think in terms of distance, you can see this is distance from closer at 20 kiloparsec, and this part is at 100 kiloparsec. So it's much distant. So it's much lower signal to detect these. So when Orphan Shinab was discovered independently and later put them together, it ends here. It ends around -70. Nobody see a clear on sky over density beyond 70. So we didn't even bother to consider this part. It was more from the model that we say, okay, maybe we should try to see if there's something there. When we started, there's no guarantee. Maybe the stream just end there, right? We don't know if there's more. But what I can tell you is we actually find stars here, and it follows exactly what we predicted. Although there's some mismatch there that might explain us to constrain the dynamic friction. So some work we are working on. So there are stars we identified here, but in terms of surface brightness, the stellar density is much lower compared to this part. And that's why, and it's much more distant. So the stars are fainter. And it's why it's hard for us to discover them without the dedicated spectroscopic observation.
Okay, we have a
Thank
couple
you.
more. Sorry, we have a couple more questions. Sarah, go ahead.
Hi, really nice talk. I'm curious, like in terms of when you identify and characterize the streams, what's kind of the relative role and importance of like the kinematic information versus information that you might get from chemical composition?
That's very good question. So I think there are two parts that chemical composition is important. In terms of discovery, as I said, I start from photometry. I don't think we know anything about kinematics of chemical abundance at that time. But when we go to identify the spectroscope member for this kind of kinematic study of diamond modeling, we use metallicity as a membership classification because these stars are mostly metal pool. So that is very important because these stars are very sparsely distributed and very highly contaminated by the foreground from the Milky Way. So having some metallicity information is very important for us to identify member stars and to do this kind of fitting. And then the other side, we also do S5, I didn't mention, it's not only on kinematics, we also follow up all the bright stars with high resolution to understand their chemical composition, because like this is a dwarf galaxy, a disrupt dwarf galaxy. So we can study the galaxy formation as well from the data here. So there is another group of people in my collaboration dedicated working on chemical evolution. Alex G would be a great person to talk to, or Teresa Hansen would be another good person to talk to if you're interested in. And we find a lot of interesting results. And show here like some of the streams are globular cluster, but the metal pool that like minus 2.7, and I think another group in Pristine find a stream at minus 3.1. So it will be interesting to understand how these globular cluster ever formed in the Milky Way and how they formed. So a lot of, I think, chemical composition will be telling us something on the, not on the mass of the Milky Way, but all the dynamics of the Milky Way, but on like the evolution of the Milky Way and its subsystems. I think that's also a very important area.
We have also one more question from Stacy, so please go ahead.
Hello, that's very interesting. I want to ask you about 1,000 questions about the ellipticities and shapes and things, but setting those aside, near the beginning of your talk, you showed a nice comparison of the overdensities due to the LMC perturbation and the simulation of that. Yeah, exactly. And it seems like there's more structure in the data than in the simulation. Is that just a plotting thing, or is that teaching us something extra?
I have to say I don't know. I would say it could be like I mean, there's no error bar here in the data,
right?
Like
or on the simulation for that matter.
Right. So it would be good to check with Charlie what he thinks. But I think there are some like I would say difference or discrepancy between the data and simulation. The point here is to show the bulk idea. Like if that it's in dynamic equilibrium, we'd expect everything to be the same. There shouldn't be this 50% of change, right? So I think that is a success. While the details, I think it's a question of how good the simulation is and how good we estimate the distance here for the data and how big the error bar there are. I don't think it's conclusive from just the plot here. And definitely there are a lot of people trying to work harder on this one and this one about the halo part. I think that's definitely something people are working on for the next generation surveys.
Okay, great, thank you.
Nice. I think just for like saving a little bit more time for the second part, we can move on. So
yes, so to start the second part of the seminar, so in this second half, Professor Ting Li is going to tell us about her experience as a female, non-native English speaking first generation student on an F1 visa in a PhD program in the US. And there are kind of two goals of the second half. First, if you're a student with a similar background, hopefully you can learn some lessons and advice from hearing Professor Li's story. And then secondly, if you do not have a similar background, then hopefully the knowledge that you learned today will help you become a better advisor and mentor to students who face similar backgrounds. So thank you so much, Professor Li, and take it away.
Thank you, and thanks for this opportunity to give this talk. I have to say this is the first time. I just finished the slides, but I've been thinking about this after I got the invitation for like the past few months. So, and I think it's important to talk about this. So I hope I'll do a good job on this, and I hope it's useful of your 30 minutes on this. So we just talked about how LMC impact the Milky Way, right? And here the case is kind of similar for me. Come to US. It's not, I don't think I have some impact to US, but what I think of the way of thinking is how I survived and how I am here. And I do want to start with a few, I don't know if it's called a disclaimer or note or whatever I want to say. So what I'm going to share is very personal. It might not be applicable to you, most of you, or maybe I'm missing a lot of what what others might experience. But I think it's a good piece of information, what I wanted to give to you. And this really inspired by Catherine Johnson talk last time that she used the word, I learned that word, it's homophily, that I realized that it's important not only, right, for us to talk about all of these things, but the most important part is a lot of things you just don't know. You just talk to people that you like to, similar to you, and that's why you never know where the outside of this circle. So that's why I think the first step for us is really to talk about these and to share these. And also, I wanted, a lot of time I talk to my friends, my Western friends, and a lot of answer they reaction they will say is, oh, I feel sad, or I feel sorry, or I'm sympathetic about what your experience is. But that's not what I am asking for this group. And I'm also not really my motivation for that. I really think it would be good if you know such thing exists so that you can help people around you that might experience something similar. And also, I want to say it's not only important for the student to know about what I'm going to talk about and advise, but if you are supervising some student, or if your cohort, your colleagues are having something similar background, then you might also pay attention to that, and that's something good for you to be aware. And finally, I want to apologize if anything I said here is inappropriate. I don't think it should have some, but it could. As I said, it's the first time I'm doing this, and I really think this group will be a good place to start my first talk of this. Maybe I'll do more if I get good feedback, or maybe I'll stop if it's not a good thing to try. But I want to make sure that the discussion I give here is not connect to any politics or legality here. It's simply just share the facts that I have, and I think some of the piece of advice. Okay, so a little bit about myself. So I'm a female. I have a Chinese citizenship. I grew up in China. I did my bachelor also in China, and then moved to US. English is not my native language, Mandarin is, and I did a PhD. I don't know if it's a small college. I mean, Texas A&M is a huge, big university, but in terms of astronomy resource, I guess it's a small university on that. And I'm also a first generation student. My parents never even went to high school, but that's kind of, it's not they are not smart. It's more a special kind of history background in China. The time my parents there, they don't appreciate like education or any of those. So that's kind of what about me. And then I'm going to talk about some of the thing I'm experiencing through different category, from the easiest to the hardest, and in 3 different column here. The left column, I will share the facts, so what I experienced. And then the middle part is what I did or what I wish I did that I think can overcome some of those difficulties. And then the right column is going to be what the supervisors or what the community I think that can do to make it better. So starting with the female and first generation college student, this is probably not applicable to most of you guys. So when I was a undergraduate student in China, it's more than 15 years ago now. At least that time in China, there is such a culture that there are 3 gender. There's female, male, and a female doctor. And that's a way to show you that, because it's not for, I don't know if this still thing nowadays, but basically it is not common for a female doctor in the community, and people will not show their respect if you are a female doctor, but show they're scary. And also, like my family, they wanted me to go college, but they don't want me to get a PhD, especially a PhD in physics. So what I did is I decided to leave the country, and I wanted to move to a different country, and I don't have these kind of bias, so I don't need to face that. So that's, I think that, I'm not sure if it's easiest or not, but that's definitely the earliest one I had. And then the other thing I face is I'm not an English, non-native English speaker. And what I experienced is, I mean, it's hard to talk a language, foreign language, and also writing. And what I find the hardest is writing, in terms of we learn how to write by reading other people's paper, right? That's how we learn things. But then when I Control-C and Control-V, at the very beginning of my career, my supervisor told me I'm doing something called a plagiarism. I didn't even know that word at that time. But that's a bad thing for career and bad thing for academia. So that's something we need to correct. So what I did, and I overcome all of those, and what I put in the middle panel. So first, you need to be shameless. That's what I think for talking. You might be aware that what I give the talk past 40 minutes have a lot of grammar issues, a lot of vocabulary problems, but I just talk. If you can understand, that's all my goal. It's not the best. it should improve, but at least it should stop you talking and giving presentations. So that sometimes you need to be shameless on that. And another thing I need to, I think it's very important, is to practice your talk. The first time I give a presentation in English at like a seminar, it was not very good. And what my mentor told me is he is a native English speaker. He said, even for him, when he gives talks as a student, even nowadays, sometimes important talk, he write down every single sentence he want to say, and then organize them, rewrite them, and then present them, and then until he can remember all of those, and without that. So even a native speaker do that, then I think you also really should consider that. So practice it, practice to a colleague, practice to your friend, and do a lot of practice for talking. And for writing, another important thing is also, I think, shameless. Just write down with your own words to start, and then do a lot of corrections. And one other thing I would say I'm very fortunate to have is I have a good collaborator to help me with writing, and that helping me tremendously. So for the supervisors, I think the supervisor should make clear at the beginning that how important writing is, and they should improve their writing skill, not just doing how to coding, how to communicate, but writing. It's the number one important thing. I nowadays tell a lot of, at least Chinese students, if you do not like writing, you probably don't want to pursue a career in faculty position, because you write grant, you write paper, you write proposal, you write everything. And you need to know that at a very early stage, rather than in your 5th and 6th year that they think they need to know that. And another thing is not only helping them science, but on the science research, but also on their writing. It would be good to have those practice as well. There's a lot of writing kind of training, these kind of workshops you should ask students to take. Okay, those are pretty easy, I think, easy in a way. The next I want to talk about is what I experienced in terms of from a small college. So, I mean, again, Texas A&M is not small, but in terms of research opportunities and research topics and the resources, it's not that much. So what helped me tremendously is something joining a big collaboration. So I got a very fortunate, I joined a collaboration called the Dark Energy Survey when I was a 2nd year graduate student. And since then, I've been working a lot with the people there until I move on to postdoc. I'm working on other big collaboration. So what did the collaboration give me? I find collaborators I want to work with. I read someone's code from the people in the collaboration. I find projects, and there are routinely organized career development training on how to write a CV, how to do interview, how like the industry job look like all those career development in these collaboration. And also I find a lot of people that I never would meet, but then I can meet them, and then maybe I ask them, say, hey, can I come and give a talk during my job season? So that is a lot of things that the collaboration gave me. And also another opportunity that I had is you have curriculum speaker come talk about it. You see all the awesome work I did with Stream, but it was started when Catherine Johnston visited A&M when I was a 30-year student, and she gave a talk. I said, oh, I want to work on these. That's how it started. There are some back and forth. I work on different directions in the middle, but eventually that's where I show all of those work. And it's coming from a professor come to a university, give a talk, and nobody working in that in my department, and I choose to work on that. And then with the help from the collaboration, I find my role, and that's what I have been working on. So what the supervisor, I think, can do in this part is send your student to these collaboration meetings. There is usually these kind of collaboration meetings. You should encourage a student to go, not only just attend telecoms, but to go and meet people and find opportunities. There's a lot of hack sessions that project come from there, papers come from there. And also give enough freedom for the student to explore. That's what I had. I'm very fortunate my supervisor gives me. Basically, I define what my PhD is about, thesis is about, and I find the papers that I want to write, and I find the collaborators I want to work with in these collaborations. And I think what the community can do is in your collaboration and working group, right? You might find a lot of students just come by themselves without a supervisor because their supervisor probably even not working in the field. As for your senior, they are looking for project. You need labor to have someone working on some awesome data that you have. So give more opportunity a project to these students from small institute. Sorry, I have a lot of text here. You don't have to read. You can just listen to me talking. It's really just for me to remember what I want to talk about. And I don't have any fancy plot or tables for this part. Okay, so the next one is a bit one of the challenging things that I've faced. So there's a lot of text here, and I have 2 pages instead of 1 page. So what I'm experiencing, or facts it's not what I experienced because I'm still a Chinese, and this is still I'm experiencing. And this is about the Chinese citizenship. And it's true not just for Chinese. I know it's true for a lot of like Malaysia, Vietnamese, a lot of Asian country people as well. But I'm only speaking about what I had experienced. So it's more on probable respect for Chinese citizenship. For other passport holder, it might be slightly different. I cannot say for them. So we need a visa to visit any country. Usually the visa lasts sometime good 90 days, or sometimes you give them, when you apply, you give them a flight ticket itinerary from starting and end date, and that's what the date they give you. Any country in Europe, UK, Japan, Korea, or even Chile, Canada, like all of those. I'm talking about when I was a graduate student, I guess. So any of these countries, we need a visa to go. And this is not the hardest part, because you just get a visa, you take like a month or two ahead of time, you apply it, you submit application, it costs some money and time. The hardest part is for any F1 visa and also H1B visa. So some of the postdocs who live on, all these visas, at least for Chinese citizens, are only valid for a year. So that means if you stay in the country, you can stay for entire 5 years as a student. But if you want to leave the country and re-enter the country, you need to get a new one if expired, and it expires after a year when you get your visa. Which means for me, for example, I hardly go to any conference in Europe, not because I don't want to apply a visa to go Europe. That's easy. But for me, the hard part is once I go to Europe, I cannot come back to US. And usually what I need to go through is apply a visa abroad. And for Chinese citizens, a lot of people, majority maybe, getting this thing called admin processing, and takes several weeks, 2 months. So you don't want to spend in another country for 2 months in a hotel and don't know when your visa is going to get approved. So that's why a lot of people don't choose to go abroad to get a visa. It's not to go to a conference to give a talk. It's not they don't want to go to the place. It's not the first part that make it harder. It's for them to get back is harder. So for me, I go to Chile a lot to observe. What's good for Chile is I go observing. I had almost 200 nights in Chile, not because, I love observing too, but a lot of time is because I need to wait for 2 months to get my US visa to re-enter US. So why not just helping observing? So I usually schedule long observing rounds in Chile. And this is not something get easier now. I'm giving a curriculum talk next month in Princeton, and I cannot go because I'm going through this admin processing, which already take more than months. So that is something to be faced, seems all the time. And the other thing, financially, something you will need to find is you need to get the ticket after you get the visa approval, and that take much longer time. And then when you are ready to buy the ticket, because your visa is ready, it will cost much more. So the flight ticket is more expensive because you maybe sometimes purchase a ticket only a week or two before your conference. And sometimes you cannot go to a conference, take the cheapest flight. For example, I'm going to Germany next week. If you go fly through US, it's only $1,500, but now I have to pay $3,000 because I need to fly to Germany directly because I cannot enter US. So these are the financial costs that I think that you have to face, or some of us have to face, either because you purchase at the very late time or because you have to avoid going through certain country. And finally, Chinese citizenship are not allowed for dual citizenship. So if I give up my Chinese citizenship, then so for example, I take a Canada one 10 years later, if I'm eligible for, I will have trouble to visit my family in China. So that's something we would need to face. And the last one I list here, I think it's important for you guys to know, although I didn't personally have that, is, for example, we had a case that a Canadian university had shortlisted a Chinese citizen. But the visa process right now takes 6 to 9 months. So while all the other shortlist candidates is visiting on site, this person have to come visit virtually. It's not equal or fair, but that's best can do. All the candidate just missed this interview chance completely. So these are the things we are facing, and what I think can do a bit to help you to leverage these. First, I did not going conference abroad. Yeah, that's what I did most of the time for my graduate school. And I go to Chile to stay more than 2 months to get US visa, which I mentioned earlier. Luckily, I had a Canadian tourist visa, and Canadian tourist visa, although it takes so long to apply, it's valid for 10 years or valid until your passport expires. So it was lucky for me, actually, I had one for tourism purpose earlier. So when I got a faculty position interview at Toronto, I could come immediately. So that's not a problem I faced, but I know a lot of people faced. But the things I wish I knew that I did not do is I should do something like a coordinated visit when I have a visa. For example, I got a Schengen visa for visiting Europe. I just go to a conference, but I would tell also some of these students what we should consider is we should contact people saying that, oh, it's very hard for us to go to a place to visit. So can I combine a trip not only to give a talk or to attend a conference, but also visit your place for an extended visit or something? This can be excuse or stepping stone for you to reach out to different institute. And that's something I would encourage international students to do. And what I think the supervisors can do, so if your student asks you a plan to go to, they want to go to a conference many months ago, don't be surprised. Even the conference won't happen in a year or in 6 months or in 9 months. They want to go and they are starting to plan it. It's normal because some, like I said, Canadian visa takes 6 months for you to get, at least now. So they need to start planning early, and also be aware and understand that your student or your participant might not be able to attend a conference due to the visa delay. And try to pay the visa fee if possible with your grant. So I spent over 2,000 now this year to pay 3 visa, UK visa, Schengen visa, and a US visa, and one got delayed. Sometimes, like one of our students here from Vietnam, he needs to go to Japan for a conference from Toronto, but there's no direct flight from Toronto to Japan. It has to go through US. So he had to get a US visa, but he had to pay that US visa himself, which is unfair for him, but because it's not related to the research directly. So this is something that he faced. So what I would suggest is try to have your institute, if you have some funding, then set up some visa fee or additional travel cost for international students and postdocs. So it doesn't burden the supervisor, right? You don't want the supervisor to feel, I need to pay extra money for the students, so I prefer not to take them. I need to speed up a bit. And then what community can do, if you are SOC or LC on conference, then give enough time for visa application. If you only give like 2 months for people to apply visa, usually they won't be able to make the conference. And try to give travel grant to those who need additional fund for visa and flight. Like for me, right, going to my next trip cost me like something like $7,000 Canadian dollars for going to a conference in Europe, because all of the travel and the complications. And if someone say they cannot travel, understand them. And if you know someone is visiting an institute near you under one visa, then try to invite them and ask them to stop by. So make their trip more efficient. And if they reach out to you, say, if I can visit your institute because I'm already here, then try to accept them if you can and help them. Okay, so that's what I think. It's a pretty big challenge, but I actually never think it was that hard. It's something you can overcome. What is actually my biggest obstacle in my career is none of the above. It's not about nationality, it's not about language, it's not about small institute. It's about the following that I currently realize is, and you get senior and senior, you will feel this stronger. At least I realized this when I was a postdoc. So my last name is the most popular name in the world. I think it's almost in the world probably, is Li, with 10% of Chinese population. So in the world, there's more than 100 million people with this last name. And in China, if you cite a paper, it's always cited by full name. However, here we only cite the last name. Yeah, in any publication here, we only cite the last name in the main text. And in any presentation that you hear, or most of the presentation you hear, you will have, no one will put the full name and to cite a figure or a plot, right? So it is about the exposure, visibility, and reputation. And when you get, it's probably not about your graduation or getting a fellowship, but it's important in terms of get a keynote talk, get tenure, get award, get medal. And that's something that I think is important and you need to think about. I put a sentence here, right? TD Li is nobody if everyone just call Li. Nobody know what you mean by Li. And that's a thing we need to face. And I was thinking about hard on this as time goes, and I want to share to people what I did and what I think I wish I did, and hopefully people like me can realize these at an early stage. So I first decided to create a middle name S. So you may see TS Li several places. I just made up an S. And I did that simply because I want to find my own paper in archive, in ATS. I don't know how to find them. So adding a mid name helped me to do that. And when I was a postdoc, I realized this. I said, okay, I need to create a collaboration that I'll need to make the collaboration shine, but not me, because I cannot get Li shine. There's too many Lis. That's what I did with S5. What I didn't do, which I would do, is I did not know until recently is your real name has nothing to do with your publication. You don't have to use anything on your passport on this. If I could choose 10 years ago, I will call my publication something like this. It is unique, maybe not that unique, but it is more unique than Li. And it is the way how we cite, or in the Chinese journal is Li Ting is like what everyone cite like their full name in paper. So I think that is a very good way to do the citation, to kind of keeping all of those. And I want to make sure that that at least people like me, not every Chinese, I think the people who has common last name would consider something like this. And I do want to say like what community has been doing and what I think we can do better. So there are Chinese characters in AAS journal. Does it really help? To me, the answer is no. The characters mean nothing to the people who do not read Chinese. So it doesn't really help for recognition and reputation. There is ORCID number. I think people are saying, oh, that is unique, so you can use that. But nobody cited ORCID number in a talk, right? So you won't be able to remember just the numbers by someone's contribution. Can we have a full name citation in the publication? I think that's probably something viable we can advocate. I don't know how easy it is, but that's something we can consider. In the talks that everyone does, if it's a common name, then probably consider putting the initials to distinguish people. I've seen like one talk, people cite Li, 3 different Li, but it's all called Li at all. So you have no idea what that work is coming from. So try to add initial there. I'll tell the student to consider this way that I'm thinking about, that I'm telling my student to consider nowadays. Okay. So I think I spent more than what I expected. I was thinking for 20 minutes or less. So this is all what I want to share. I hope it's useful. I hope it's not too discouraging. I hope it's inspiring and let you know at least some of the things we are facing. And maybe it's not just for me, it's for many international students that near you. And also want to make sure that if you are a professor, after you listen to this talk, it doesn't discourage you to taking international students and think they are trouble. I think they are awesome. And I'm also happy to reach out if you have any further questions, if you want to chat in a future time. Okay, I will stop here.
Thank you so much for this talk. I know I learned a lot. I'm going to stop the recording right now.